All right, so yesterday we talked about intermolecular forces, and we said that that's basically describing how molecules stick together in space. And we started out talking about a handful of them. So let's go back and talk about the main types. The first one that we had was dispersion or van der Waals or London dispersion or instantaneous dipoles. That describes the attraction between two nonpolar molecules, and it's due to a momentary imbalance of electron density. And we said this is thought of as a weak force, but it really depends on the surface area involved. If you have a lot of surface area, the things get pretty sticky. All right, dipole-dipole forces are the next up, where it's the interaction between two molecules that are polar or have net dipoles, and we need to know the three-dimensional shape before we can determine that. And then we said going further down, we've got hydrogen bonding, where it's a type of dipole-dipole interaction that's really strong. It's where a hydrogen atom is shared between a lone pair and an electronegative atom, like fluorine, oxygen, or nitrogen. So my trick is if you see a hydrogen coming off of fluorine, oxygen, or nitrogen, then it can H-bond. And then we talked about a bunch of cool features with hydrogen bonding. Today what we're going to do is talk about the relative strength of all of these and make a chart. So I'm going to put weak up here, and then we're going to go down. What was the weakest intermolecular force? Was it H-bonding, dipole-dipole, dispersion? Dispersion, exactly. And then we said with dispersion, you essentially have this momentary imbalance where one side of a molecule is electron-rich, the other side is electron-poor. So we'll have an electron-rich side of this molecule over here, and then same thing on this one. I'm going to do delta symbols to show imbalance of electron density. Whoop. And we said that this, whoop, man, my pens are slow today. This is the attraction between these two. So attraction between nonpolar molecules can lead to dispersion forces. All right, so dispersion's that first one. Like I said, it depends a lot on surface area, which is why I have weak in quotation marks. Sometimes this can be rather strong depending on how much surface area is involved. All right, so that's at one end. Next up, we have dipole-dipole. And with an example of this, I'm going to show a molecule down here. This is acetone. Acetone is used a lot in nail polish remover. So if you ever get that smell of nail polish remover, that's acetone. If we look at this molecule, it does have a permanent net dipole pointed up, right? So that oxygen is basically hogging electron density away from the carbon underneath it. So the dipole is pointed in the up direction. And this will essentially stack with another acetone molecule because this one also has a net dipole pointed up. So just like before, we've got this interaction here between the partial positive end of one molecule and the partial negative end of another molecule. So this is a much stronger interaction than your typical dispersion force. All right, as we go down, the next one that we run into is a special type of dipole-dipole, which was H-bonding or hydrogen bonding. And hydrogen bonding is still between two polar molecules, but this time we have an H on the phone. And like we said yesterday, a good example of this would be water. If we think about this, right, this oxygen is pulling electron density away from each of these hydrogens. So there's a very strong net dipole. But what ends up happening here is an attractive force between this lone pair on one of the water molecules and a hydrogen. So it's attraction between a lone pair and a hydrogen that is on the phone. All right. So those were the ones we covered yesterday. However, there are a couple more that are a little bit different, a little bit unique. The next one is actually an ion dipole. And it's exactly what it sounds like. What you have in an ion dipole situation is you have an ionic compound that's combined with a dipole, or a compound that has a dipole. So this would be a mixture, not a pure solution. So let's say we've got something like a cation. A cation is going to be attracted to things that have a negative charge, right? Or at least a partial negative charge. So if you put a cation into water, what ends up happening is the oxygen, because it has so much electron density, really likes to basically snuggle up against that cation. It's the technical term. So really what's happening here is an interaction between a partial negative and a full positive. So it's the attraction between an ion and a polar molecule. This actually explains why when you throw something like sodium chloride, which is ionic, into water, it dissolves, right? So essentially the water will wrap up the cation, which in the case of sodium chloride is sodium. And what do you think happens to the chloride, the anion? It's basically going to flip around, right? So with an ion dipole, you could have both situations. So if you have a negative charge, the oxygens won't be facing it. Instead, the hydrogens will, because they're partial positive. So those hydrogens will basically hang out right near that negative charge to help stabilize it, right? So it's this electrostatic interaction between the full negative and partial positive. All right, so those are pretty strong. Next up, after that, is just simply an ion-ion interaction. This is often known as an ionic bond. And there are a few more after this, but we're going to kind of stop at these. But an ionic bond is still an intermolecular force. What it is it's the attraction between a cation and an anion. These are really, really, really strong. They don't want to be ripped apart unless you put them into a solution. So these are the strongest. Which makes sense too. Have you ever boiled sodium chloride by itself without water? If you put it into a skillet and crank up the heat, will it boil? No. It takes a lot of energy to actually get something like sodium chloride to boil on its own. All right, which leads me to my next point, and that is that stronger intermolecular forces lead to higher boiling points. So that's our big takeaway from this chapter, is we have to be able to predict which intermolecular force we have and then compare them in terms of boiling point. So let's go and compare. If we think about an example of dispersion forces, that would be something like helium in a balloon, right? It's pretty easy to boil helium. It's already a gas. But if we tried to turn something like sodium chloride into a gas, that takes an enormous amount of energy, thousands of degrees Celsius, to actually vaporize sodium chloride. All right, so we have one last part of this chapter, and that describes intermolecular forces in solution. And like we said before, we can have a solution where we have a solvent dissolving a solute. How do we calculate the concentration? What's the unit? Yeah.
Molarity, which is moles per...
Yeah, exactly. So we can calculate the amount of solute in solvent by using molarity. So calculate the moles of solute in liters of solution and quantify that. However, sometimes it's hard to predict what two items will mix together well, right? So if you mix oil and vinegar, they don't mix, right? They'll float on top of one another. But if you mix sugar and water, they will mix. So then the question is, well, why do some things mix and other ones don't? And so I've got a really good generic predictor, and that is that like dissolves like. And what I mean by that is that molecules with similar intermolecular forces will dissolve in one another. Another way of saying that is they will form homogeneous mixtures. What does it mean when I say homogeneous? It's got to be the same throughout, right? Sorry, I didn't mean to cut you off there. All right, another term for a homogeneous mixture of two like things is miscible when you're talking about two liquids. So this can be called a miscible solution or miscible compounds. Okay. If the IMFs are similar, meaning not exactly the same, then sometimes they will mix. So an example of this situation would be sodium chloride and water. Yep?
On the top one, would that be molecules with the same IMFs?
Yes.
The point is if the IMFs are similar?
Yes, exactly. So the top one, and we could say molecules with similar or the same intermolecular forces will form homogeneous mixtures, usually, meaning they'll be miscible. So if you want, you can swap out similar for the same. For the bottom one says if they're similar, meaning not exactly the same, sometimes they will mix, sometimes they won't. So yeah, let's just even change that to avoid confusion. So if we think about sodium chloride, the main intermolecular force is that ionic attraction between the sodium cation and the chloride anion. If you put it in water, water's main intermolecular force is H bonding, but they mix together, right? They're relatively strong intermolecular forces, so they will mix even though they're not identical to one another. So that's where I say like dissolves like, not same dissolves same, right? All right. Last but not least is if the IMFs are really different, then they won't mix. And if you have two liquids, typically what will happen is you get a layer separation, kind of like with oil and vinegar, right? So oil in this case has a very different intermolecular force than vinegar. So let's take a look at some of these examples. So on the left, we've got oil being added to gasoline. So if you ever work with a 2-cycle engine, you might have to do this. So a motorcycle or a chainsaw, something like that. And if we think about oil and gasoline, they both have really similar molecular formulas. Both are hydrocarbons, meaning they're made up of carbon and hydrogen almost exclusively. So I'll call that CXHY. We don't know how many carbons and hydrogens, so I'll just throw in variables there. What's the main intermolecular force for a hydrocarbon? Would it be dipole-dipole, hydrogen bonding, dispersion, ionic? What do you think? If it's only carbon and hydrogen, is there going to be any sort of imbalance of electron density? No, they have really similar electron densities. So there's no polar bonds in this. That means the molecule can't be polar, which means it must be dispersion, right? Okay, so both have dispersion. That means they will mix. So it's a pretty easy predictor. The next one is that oil vinegar situation we were talking about. All right, so let's describe what the oil is. If we think about oil, it's actually pretty similar. It's mostly a hydrocarbon. So it's CXHY, which we said was dispersion. All right, and then vinegar. Let's draw out the actual compound for vinegar. So this is the molecular formula for vinegar. In addition to there being water in it, you normally don't drink pure acetic acid, which is shown. What's the main intermolecular force here? Do you think it will be dispersion anymore? Probably not, because we know they're not mixing. All right, then we go to dipole-dipole. Is there a permanent dipole in here? I'd say yeah. The oxygen's really electronegative, so it's going to pull electron density away from that carbon and away from that carbon and away from that oxygen, right? So those oxygens are really greedy. They're going to hog the electron density. All right, so it definitely has dipole-dipole. Does it have anything else that's stronger? H-bonding, right? We've got a hydrogen that's on the phone. So what I like to do anytime I see that is just to highlight it, right? So this one can H-bond. Because dispersion is so dissimilar from H-bonding, these will not mix well together. All right, and then the last one that we've got is wine. So wine is almost all water, right? If you look at a bottle of wine, the percentage of alcohol in there is typically like 10 to 15%, but it's not 100%. You don't want to drink 100% alcohol, that's for sure. All right, so the first thing that we have is water, which is pretty easy to remember, the Lewis structure for water. And then we also have ethanol, which is a unique alcohol. It's got 2 carbons coming off of it, an oxygen and a hydrogen. So in water, we already said that the main intermolecular force is H-bonding. What about with ethanol? Looks like it would also have H-bonding right there too. We have a hydrogen on the phone. So both can H-bond. Which is why when you mix alcohol, like ethanol, into water, it will mix. Does that make sense? So we do have to know a lot about the overall structure of molecules before we can make a lot of these determinations. All right, there's a couple of weird examples. The first one I showed you was ionic compounds dissolving in water. And even though an ionic bond or ionic attraction is much stronger than H bonding. Like we said, those water molecules will essentially wrap up each of those ions. So let's make a second note of that. So some ionic compounds will dissolve in solvents that can H bond. This is an example of ion dipole. So basically those water molecules will go and basically wrap up one of these ions and rip it away from the crystal. Yep.
But the same process doesn't happen in, say, ethanol, which can also H bond.
Yeah, so that's why I said some solvents or some ionic compounds will dissolve. It really depends on the situation. So not all the time, but some of the time. If you go on and take general chemistry, you'll actually talk about solubility rules. There's a whole bunch of rules. We're just not going to cover those in this class, though. Yeah. All right. My last example is one of my favorites, soap. And soap is weird. And what I mean by that is if you look at soap, what you have on one end, typically, is something that looks like this. This oxygen has a formal negative charge. Then you've got a CH2, 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 and these CH2s go on for a long time. So in fact, I'm just going to bracket one of these and write N, meaning it's a repeating chain. And it goes on for sometimes tens or hundreds of units. So this is a really long soap molecule. And if we look at this end, it's very polar. That means it will dissolve polar things, right? Or polar molecules. However, this end of soap, basically from this carbon over, is very nonpolar. Meaning it will dissolve in nonpolar molecules. Oh, sorry. You zoom back in. So basically, there's this duality to soap. You've got one end that really likes to be near polar things, one end that likes to be near nonpolar things. And what ends up happening is this forces soap into a sphere shape, right? So what we basically have on the outside is all of these polar heads. So that red unit is going to be sticking out near water. And why do you think it's attracted to water? Yeah, water is also really polar, right? So the polar red region that I've highlighted is going to be attracted to polar water molecules, basically form a protective shell. And then all of the non-polar regions are basically going to point into the center because they don't want to be near the water at all. They have really different intermolecular forces, so they'd rather just kind of hide in the middle of this shell. The great thing with this, though, is let's say you're doing dishes and you've got a greasy pan with a lot of oil on it. That oil droplet can be wrapped up in the middle of all of those green tails because the green tails are also nonpolar and attracted to that oil. So the oil will basically be trapped on the inside of this big sphere shell-like structure. So oil can get trapped inside. These are often referred to as emulsifiers, meaning they allow two unlike things to mix. So oil and water in this case, you can actually mix together in a soapy solution and form a somewhat homogeneous mixture. Does anybody remember a few years ago the big oil spill in the Gulf? Yeah, that was a huge deal. When you have an oil spill, the oil will float to the surface of the water and hang out there for a while, for a long time actually, and that causes a variety of problems. So you've probably seen pictures of birds that were coated in oil or sea life that was coated in oil. So there was concern about that, obviously, and so what they were trying to do is to figure out, what do we do with this oil if we can't scoop up all of it? They tried to scoop up as much as possible, but you just run into physical limitations. So instead what they did was they basically designed a bunch of special soap molecules and then sprayed it over the ocean, and the soap molecules basically encapsulated that oil into these little micro droplets, and then that would sink down to the bottom of the ocean. And the thought was, at least, that microbes in the bottom of the ocean would actually start breaking down that oil, and then the sea life on the surface wouldn't be exposed to these giant oil slicks. What they're finding out more and more was that was a decent plan, there was good intent, but having a big oil slick on the bottom of the ocean causes a lot of problems too. The microbes aren't that fast at breaking down the oil, so it just moved the problem from one place to another place. So it's a pretty interesting utilization of soap technology. There's other soap too, where instead of having this sort of group on the end, you've got sulfur and some oxygens off of there. So if you look on your soap containers at home, it might say something like sodium lauryl sulfate. That's a different type of soap, but same idea. You've got a charged region on one end, typically anionic, and then a nonpolar tail coming off. Any questions? Nope. All right, so let's do a few practice problems, and then once we're done with that, I might let you loose to work on your pod. All right, so the following characteristics, solid state, high melting point, crystalline structure, and soluble in water describe which type of compound. So check with your neighbor and see if you agree. There's one important word in here, so I'll underline that. Crystalline. What does that mean? It means it wants to form a crystal, right? Do all covalent compounds want to form crystals? No, water is a covalent compound. It does not form crystals. Molecular things, it's kind of generic and nebulous. I mean, a lot of things are molecular, but some, like water, don't form crystalline structures. Other ones do. Ionic compounds, do those form crystals? Yeah, things like sodium chloride are actually crystals of sodium and chlorine in this big three-dimensional network that looks like a brick wall. So this would be the most appropriate answer for that one. It's the attraction between cations and anions that leads to that big brick wall. Schematic, I don't even know where they were going with that one. They just threw that one in. All right, which of the following will exhibit the intermolecular force of hydrogen bonding? This one should be pretty easy. We've seen a bunch of examples. Well, the first one? No, we don't have a fluorine, oxygen, or nitrogen, so that won't work. B, we don't have a fluorine, oxygen, or nitrogen, that won't work. Same thing with C, but D, we do have an oxygen there. Therefore, this would be a good example of something that can H-bond. All right, which of the following substances will be the least soluble in water? This one's a bit harder. So I'll give you a minute to think about it and then check with your neighbor. So meaning which one won't mix well in water? I will give you a hint. Water, we just said, can H-bond. Give me a thumbs up if you think you've got this one. A few people? All right, so let's think about it. NaCl, that's salt. Salt dissolves in water, right? That's an easy one. The next one, will this dissolve in water? This is called ethylene glycol. Why do you think it will dissolve in water? Yeah, if we look at this one, looks to me like it can H bond, right? It's got a hydrogen coming off of oxygen, so it has the exact same intermolecular force. It should mix well. All right, what about C? What's the main intermolecular force there? That's benzene. Yeah, it would be London dispersion. There's no polarity at all between carbon and hydrogen, really, or at least not a significant amount. So this one would be London dispersion, or just dispersion. So chances are these will not dissolve, but let's check the last one. NH3, what's the main intermolecular force here? H bonding, right? If you ever smell something like Windex, when you clean your windows, that has dissolved ammonia in it, so it forms one homogeneous mixture of liquids. So things like oils won't mix with things that H bond. All right, so for the rest of the class period, I'll let you get a start on your problem of the day.